Okay, good afternoon. My name is Matt Robinson, Environmental Protection Specialist for the DC Department of Energy and Environment. On behalf of the Planning Committee, I welcome you to the second day of the MARCO Mid-Atlantic Marine Debris Summit. Today, we will focus on the latest information on microplastics and microfibers and their potential effects on human health, wildlife, and their ecological impacts, as well as some innovative projects to reduce those impacts. Later today, we will tackle derelict fishing gear and innovative efforts for removing or preventing this type of marine debris. This summit is made possible through a grant from NOAA's Office for Coastal Management to the Virginia Coastal Zone Management Program. The Virginia CZM program contracted with the Mid-Atlantic Regional Council on the Oceans, or MARCO, to help develop this summit. As a member of the Mid-Atlantic Marine Debris Work Group, I would like to thank our summit planning team. Laura McKay and Virginia Whitmer of the Virginia CZM program, Avalon Bristow and Judy Tucker of MARCO, Katie Register and Michaela Jennings and all of their colleagues at Clean Virginia Waterways of Longwood University and the university's event and conference staff who have helped with technical aspects of this Zoom meeting. Christy Kehoe with the NOAA Marine Debris Program, Christy Mazzeo-Fortner with the New York Department of State, and Carl Vakoba from Monmouth University. Before we hear from our opening speakers, there are a few housekeeping matters. Your cameras are turned off and mics muted, but we do ask for and appreciate your engagement and encourage you to participate in our polls and write your questions into the Q&A box, not the chat box, the Q&A box, for any questions that you have. We will be recording the summit and it will be available later on the MARCO website. The goal of this week's summit is to inspire and empower our partners in marine debris reduction. We will be hearing updates on current marine debris science and trends, and we'll explore techniques and tools that are effective in enhancing knowledge, changing behavior, and influencing policies that reduce marine debris. We are excited to be working with all of you, our Mid-Atlantic partners, as we explore regional efforts to reduce the sources and impacts of marine debris. Now, with that out of the way, let's discuss a little bit about microplastics. Okay. Microplastics and microfibers. Many of you are probably very familiar with this subject. Otherwise you would not be dialing in today. I'm in Washington, D.C., the nation's capital, and D.C. is a coastal city. We have tidal waters, and one of our major rivers is the Anacostia River, which has been trashed for a very long time. And we have been working for many years to do things to reduce pollution in the river, such as implementing a long-term control plan to reduce combined sewer overflow, stream restoration, wetland restoration, and reducing trash. And beginning in 2010, we actually established a total maximum daily load, or TMDL, for trash for the Anacostia River with EPA and the state of Maryland. A TMDL is basically a pollution diet. It assigns loads to our local municipal separate storm sewer system, combined sewer systems, and non-point sources, which is attributed mainly to illegal dumping. For the district, our total annual reduction is approximately 217,000 pounds, but it only addresses trash greater than or equal to an inch in length or diameter. As you can see in the picture on the left-hand side, you see a lot of bottles, styrofoam, other plastic pieces. This is the stuff we're mainly trying to keep out through the use of the TMDL. Well, what about the small stuff? Is there evidence of microplastics in the Anacostia River and throughout the rest of the Chesapeake Bay watershed? I think the answer is yes. As you can see from this picture, on the left-hand side, all the little individual tiny bits, so white bits that look like snow, those are actually individual polystyrene particles that we found in one of our trash traps along the Anacostia River. This is a particularly acute example of microplastic pollution. What we think happened here was that there was probably some packaging in the storm sewer drainage area to this outfall. That packaging broke down, blew all over the place, ended up in the storm sewer, and this is what we ended up with. So we wanted to look into this a little bit more to see if there's in fact severe impacts from microplastic pollution on district waters. Right here, this is a submerged aquatic vegetation bed, or SAV bed. Others refer to it as submersed aquatic vegetation, or seagrass. This is a native bed of water stargrass back in 2017, just south of the Reagan National Airport on the Potomac River. And as you can see, it's full of trash. Myself, as well as Bob Murphy from Tetra Tech, who you'll hear from in a few minutes, and Fong Tru from the Metropolitan Washington Council of Governments. We put our heads together on this and thought, what if SAV beds are actually acting as traps for trash and other plastic particles? A lot of microplastics come from the breakdown of larger macroplastics, such as the things you see in this picture. So in DC, between 2009 and 2017, we actually had a 2,000% increase in SAV. It was huge. We met our goals for a partnership we're members of called the Chesapeake Bay Program. We're concerned about restoring SAV because it's habitat for a lot of important critters. As you can see the snowy white egret here feeding in this bed, but it's also habitat for our state fish, the American shad. So we had a question, could SAV beds be capturing microplastics? And we did a study sampling inside SAV beds and outside in the water column at several sites in the Potomac. And we found a significant difference. Definitely in vegetated areas, there was a higher concentration of microplastics than in unvegetated areas. Evidence of microplastics elsewhere in the Chesapeake Bay. Well, in 2014 to 2015, a group known as Trash Free Maryland worked with the University of Toronto and other partners to conduct mainly a volunteer-led trash trawl of the Chesapeake Bay main stem, mainly in Maryland waters, from the city of Baltimore all the way down to the mouth of the Potomac. Hopefully folks can see my cursor here at the very bottom. That's the mouth of the Potomac. Point Lookout, or actually that's actually Smith Point right there. They trawled 30 different stations, and 100% of samples that were collected possessed microplastics. So the highest concentrations, and this has been confirmed by other studies done elsewhere, were found in urban and suburban tributaries. So I think some of the highest concentrations were found in the Patuxent, which gets a lot of urban runoff from the DC metro area, as well as Baltimore and the Patapsco. So I'm a member of a group at the Bay Program, the Chesapeake Bay Program, known as the Submersed Aquatic Vegetation Work Group. Myself and Bob Murphy, who's going to talk in a minute. We're both members. We took this to the SAV work group and said, hey, you know, we're spending millions of dollars every year to restore SAV habitat in the Bay. It's important for fish, crabs, other things, but it might be accumulating microplastics. How do we bring more attention to this issue? So we applied for a grant from what's known as the Scientific and Technical Advisory Committee at the Bay Program to hold a workshop in 2019 about microplastics in the Bay and the watershed. This is actually a link to the stack report. I believe these PowerPoints are going out or be posted, but you can read the stack report online. It contains all kinds of great information, including several recommendations that came out for the Bay Program to act on to address microplastics more. Progress to date. We were authorized to create a plastic pollution action team at the Bay Program to address recommendations in the 2019 stack report. We have a diverse group of members from federal agencies, universities, and research institutions, as well as the Bay Program advisory committees. Our focus right now is to get the science straight. And in 2021, the PPAT, we call it, developed a preliminary ecological risk assessment of microplastics in the Potomac River and a science strategy for directing future microplastic research in the Chesapeake Bay and watershed. And Bob's going to talk more about that in a minute. So outline for this session today, what are we talking about today? So we wanted to emphasize two main themes: potential ecological and human health impacts and pollution control measures that are being taken. We will hear from Bob Murphy, Tetra Tech, on the development of the ecological risk assessment for microplastics in the Potomac. Dr. Sherry Mason from Penn State, I was fortunate enough to sit on one of her talks back in March, a talk she gave for Penn Environment on all of the microplastic sampling they've been doing up there. And she has some great information to share on, it's actually rather disturbing, on the impacts of plastic pollution on public health. Dr. Chris Perkins from the Hampton Roads Sanitation District, he and his colleagues down at the HRSD are doing some really innovative work to implement microplastic controls in sewage treatment plants. And finally, last but not least, Rachel Miller, who's actually outside of the Mid-Atlantic. She's up in Vermont or Maine. I can't keep track of her half the time, but she's somewhere on the water. And her group, the Roselia Project, has been doing some great work on microfiber controls and laundry. You might be familiar with the Coreball project. So Rachel will talk more about that in a minute. So with that, I would like to hand it over to Bob Murphy. I'm going to stop sharing my screen, Bob, so you can share yours.
All right, thanks, Matt. I'm going to also keep my video off to preserve bandwidth. You don't want to look at me anyway. Let me pull it up.
I was going to say no comment, Bob.
I know. Okay. It's funny, as we've been doing this for a year and a half now, I still have to adjust to each of the platforms we use. So pardon me while I start this. Okay. Not hearing anything that you can't see. I hope everyone can see this well. And thanks, Matt. That was a good intro to this talk, because it does follow on the work that we've done regionally in the Chesapeake region, and moving forward with the development of a risk assessment conceptual model and science strategy for the Bay Program. Should take a minute here to recognize some co-authors on this work, because it's been a very strong group effort. Jennifer Flippin with me at Tetra Tech, although she has now moved on to the National Park Service. Ryan Woodland down at Chesapeake Biological Lab, University of Maryland. Matt, of course, is instrumental as chair of the PPAT, and Kelly Summers, his vice chair of the PMAT with Region 3 of EPA. So I'm just actually reiterating, Matt, you and I should have probably compared notes, but that's okay to reiterate this. As Matt mentioned, in 2019, STAC released the report from our workshop on microplastics in Chesapeake Bay, and this was really to examine the state of the knowledge and gaps and data gaps, and what we understood, or what we, to borrow a phrase from the late Don Rumsfeld, what we understood that we didn't understand, sort of. And based on those recommendations that came out of that report, the management board of the Chesapeake Bay Program authorized that creation of the PPAT, as Matt alluded to, which coalesced in spring of 2020 and held our first meeting. This is a lot of text here, apologies, but again, this is going to be available in a PDF after the conference is over. But there were some assignments from the management board for the purpose of the PPAT to give it some direction. So that was to provide the oversight of the preliminary ecological risk assessment. That was listed as a priority. And then based off of the results of the risk assessment model, to develop a science strategy that would identify and prioritize gaps. This is a direct result of the workshop that we held. And then we have to come back to the management board, which we have done, to present the results from the risk assessment to decide what's our next avenue, what's the next direction that we're going to go in, and what do we need to do and prioritize. And then simultaneously, the fourth idea here is to monitor the policy advances. So directives from the different governmental agencies in the watershed, what's being done to actively manage plastics and plastic pollution. I want to focus primarily on this one today. It's to talk about the development of the risk assessment and how it informed the science strategy that was eventually developed. A little background on how we got to the risk assessment. So what we did is we focused, the nature of a risk assessment is to develop a biological endpoint. In this case, the PPAT decided on striped bass for several reasons. It's an apex predator. That means what it consumes is often going to be a reflection of all of the prey items available to it or its prey. So it's a good indicator of what might be the levels of microplastics that might be entering the food web. There's also a wealth of knowledge on striped bass in the Chesapeake region. It's an extremely well-studied species. We understand diet, we understand ontogenic shifts as the fish grow from egg to larval to juvenile to adults. And it's not lost on us that it's an iconic bay species. It's a very popular sport fish, probably the most popular sport fish in the bay, historically and currently. It's also a management success story, historically. Those who may be unfamiliar with the striped bass issues of a few decades ago, the population in the bay absolutely crashed in the late 80s, and a complete moratorium was put on fishing for them, which was unheard of at the time. Took a lot of political risk to do that, but was ultimately successful, and the population, the spawning stock rebounded. So it's considered a very strong success story. Also, that striped bass, over roughly 70% of the striped bass population along the East Coast, so that's from Florida up into Canada, are spawned in the Chesapeake Bay system. So it's an extremely important nursery area. So that was why we looked at striped bass, or chose striped bass. Now, the Potomac River, instead of using the entire Chesapeake Bay watershed, we focused on the Potomac. Large part, the reason of that was, the issue of scale. The Potomac is a smaller watershed, and we're focusing only on the tidal portion, I should point out here. Although we certainly recognize that sources in particular are going to be coming from the non-tidal region as well. But because we chose striped bass, we were going to be restricted to the tidal areas. The Potomac is often considered a microcosm of the Chesapeake Bay writ large in terms of estuarine structure. It's tidal fresh, oligohaline, several salinity zones, several habitats that are found elsewhere throughout the Chesapeake system. And as I mentioned before about the nursery areas for striped bass, the Potomac, outside of the upper Chesapeake, the Potomac is the second most important nursery area along the entire East Coast. So it is a very important region to understand the dynamics and possible impacts that microplastics might be having on the species. So this is a graphic showing the ecological risk assessment model input and the criteria for inclusion for Potomac River striped bass. And you'll see here, I've noted we did put some age brackets on striped bass. So we were only focusing on 0 to 2-year-olds. The reason being is when striped bass are spawned in the riverine system, they will spend the first 2 years of life in general in the system before they begin their migratory habits. So those unfamiliar with striped bass life history, they're highly migratory. So if we use adults, the understanding might be confounded by the fact that they leave the Chesapeake Bay and migrate up and down the East Coast. So we wanted to restrict it, our age classes to just 0 to 2-year-olds. It's included a full literature review. We wanted to prioritize Potomac River data should it be available. And secondarily, Chesapeake Bay and other tributary studies in the region. We did look at, then third and fourth, we looked at other studies just to give us an idea what other dietary pathways might be out there from along the East Coast and even globally, since striped bass have been introduced elsewhere historically. The figure on the right shows the boundaries for the salinity regime for the Potomac River. So as you go, the upper part of the tidal river up towards DC would be tidal fresh. Then we have followed by oligohaline, and then the mesohaline is the lower part. And that's going to be important because there's a species turnover as salinities change and prey availability for striped bass changes. And we'll show that. That was actually of particular interest to us if we're going to identify the correct trophic pathways. So to develop the model, we identified the biological endpoints of potential interest here. So in this case, for striped bass, this is actually less complicated than it first appears. So in the purple, that's the year classes of, or age class rather, of striped bass that we were focusing on. And then just the different trophic levels that constitute the prey network. So the environmental microplastics pool will be the orange. So this is microplastics entering the system through the water column, or conversely may have been buried in sediment. So they'd be available to benthic organisms, burrowing organisms. Likewise, as they move up in the sediment, detritus, phytoplankton potentially, certainly zooplankton, but that would be the invertebrate prey into the prey network. Don't get too caught up in that. It's more of that's just a generalized figure there. On the right, on the other hand, is what are some parameters that are of particular interest with the risk assessment. The individual endpoints, for example, so this would be on an individual fish. Is there an effect on growth rate of a species, of a single fish from microplastic ingestion? Fecundity, are they having reproductive success or not? Is there direct mortality? Are they starving because they have too many microplastics in the guts? On the other hand, we are also interested in the population assessment endpoints. So this is particularly important for fisheries managers. So things like catch per unit effort, is that being affected? Is size at age, so if growth rates are declining, size at age is also declining. Age structure, are certain age classes or year classes being reduced? Mortality and spawning stock biomass are probably the two most important. Spawning stock biomass, of course, is extremely important given the nature of the Potomac River as a nursery area. For those who have any background in fisheries, mortality estimates are critical to determining how many fish can be taken in any given year from a stock. So it's imperative that we understand all the contributions to natural mortality. We can always estimate mortality from fish taken from the system through harvest, but we need to understand all the other forces that contribute to mortality. And this is where microplastics can potentially have quite a significant impact. The next, after we had accumulated most of the data through the literature review, we developed a qualitative food web. So this is just a basic, I apologize, the little formatting glitch on the picture, but it gives you an idea of just the network of prey items and all the taxa that are in the trophic web, if you will, for young of year striped bass. It's just to better understand what they're feeding on and how they're connected. But we took this a little bit further because we did have enough data to do a semi-quantitative food web interaction for striped bass. And I mentioned earlier about the salinity regimes being important. I'm going to go through those now. So starting at the upper portion of the river, so it's very similar to the prey network shown earlier in the qualitative network. But now we actually pulled some data from Walt Boyne et al.'s work done in the early 80s, where they were looking at striped bass diets in the Potomac. And they did the analysis by salinity regime. So here we see the thickness of the black line, the connection, represents the relative contribution to the diet. So you can see here, insects in this tidal freshwater area constitute a large proportion. It was 40-some% of the striped bass diet, followed by other fish larvae and polychaetes. This is very useful in understanding what the potential pathways are. In the oligohaline, if you're moving downriver, insects still very important, but now we have the appearance of mysid, shrimp, and amphipods contributing a more substantial component to the diet. And then to the mesohaline, insects become less importance, and mysid shrimp become more important, and then of course amphipods, polychaetes, and fish larvae. So that gives us an idea of the relative contributions of different taxa in different areas. So what we did next was to look at those taxa and do a further literature review globally to see what's the current understanding of microplastic uptake by those taxa. And this is just a screenshot of a table that's in the report, in the risk assessment report. What we found is all the taxa that appear in the striped bass food web model have been demonstrated to uptake microplastics. So the risk is real. So what that told us was, wow, striped bass have the potential to be quite impacted through their dietary pathways. So microplastics getting into the system can eventually work their way up. We've identified data gaps because all of those, in fact, if I go back, one of the points here, all these studies are outside the Chesapeake. So what that tells us is we have a paucity of data, but we have the potential to have some tremendous impacts. So that led to the development of the science strategy. And the purpose of the science strategy was to guide future research on the impacts of microplastic pollution in the Potomac River and Chesapeake Bay. The PPAT organized the science strategy around several questions. Questions included, how can the government and resource managers develop sound policies? I mentioned this earlier. This is to reduce plastic pollution, And there's also an idea of assessing the economic impacts of that. That's a little outside my wheelhouse, I will admit, but that was certainly a topic that bears investigation. We definitely want to, we recommended a better understanding of the sources, distribution, and hotspots. Matt mentioned in his introduction that there have been a couple studies that have looked at microplastic distribution in the Chesapeake Bay. And they all pretty much tell the same story right now. They're there, we're finding them, and they're all over. What are the health risks posed by microplastics? It's a poorly assessed topic right now in the Bay region. It has been demonstrated elsewhere, where microplastic, I believe the current estimate is we ingest 5 grams of plastic. I don't recall if that's per week or per month, but that's a lot of plastic that enters the human body regularly. The ecological health is actually is better understood globally right now. So the sources, pathways, composition, and the fate of microplastics loading into the Chesapeake Bay is of particular interest. Where are the hotspots? This is important. The diagram below, for example, in coastal areas, in estuaries, you have the river plumes coming out and developing a front. It's a turbidity maximum zone is what we refer to it as. These areas are the prime areas for striped bass and other migratory species to spawn. It's because there's a lot of biological productivity and lots of feeding opportunities because of that. Well, the same reasons, physical reasons that create the feeding plentifulness, if you will, that's a poor word, but opportunity is also the same processes that would ensnare and entrap microplastics in that same area. And that's what this diagram shows. So the models to date don't show that very well. There is model development underway out of Penn State, but that's beyond the scope of this talk. Data gaps. This was the big charge that came out of the STAC report. This is what the PPAT really wanted to see come out of the risk assessment models, the lack of experimental data. So we don't know we don't know much at all about the relevant conditions. So the exposure, what's the rate of microplastic consumption by fish in the Chesapeake Bay? We really don't even have a handle on that yet, although some studies are now underway. What are the individual and population effects? If you recall, those are particular endpoints of interest for a risk assessment, and fisheries managers in the region are very interested in these population level effects and the potential for an impact to spawning stock biomass. We don't really understand with a lot of clarity the trophic transfer of microplastics from, say, basal resources, so in the sediments or on the blades of SAV that we'd found in a previous study that Matt mentioned. And is there a spatial or temporal dependence that plays in here? Obviously, the idea is urban areas is probably going to be a greater hotspot, but these urban areas are usually the same areas just above the prime spawning habitats. So I'm thinking, Washington, D.C., Baltimore, River, for example, all these cities were founded at the fall lines. Well, it's the same areas that migratory fish are spawning. So we really don't have a good understanding of that right now. Part of the science strategy was the recommendation for a monitoring strategy. Those of you unfamiliar, the Bay Program supports between the various jurisdictions a fairly robust and comprehensive monitoring program that includes benthic populations, fish, water columns, so water quality things, nutrient loadings, et cetera. Plankton, although that I do not believe that is ongoing anymore. And the non-tidal monitoring is also quite important. And we can build with we've recommended is to, rather than create a whole new beast, is to build the microplastics monitoring into the existing monitoring programs. So the conclusions is that, and Matt mentioned these earlier, the previous studies, and they're very recent, that microplastics are fairly ubiquitous throughout the bay and the watershed. So it's a problem, but it's largely unquantified at this point. The monitoring effort we feel should be targeted and various groups should be working a little bit more closely together with standardized processes and terminology and methodologies. And we really think the recommendations in the science strategy are going to work their way up into management at the Bay Program, and really put us on a path forward to really better understand this and free up some resources to address this problem. And the first thing to do that is to understand the problem. And I think I'll leave it at that because I think I hit my time. And I see Matt on video, so that means I'm out.
Thanks, Bob. And let me apologize. I forgot to read your bio in the very beginning. So I put
That's
it in
okay.
the chat. It's a very interesting story if anyone's interested in reading it. So, please feel free. Sorry about that. But thank you for that very informative presentation. Again, we're going to keep all questions and answers to the end. So, but feel free to enter your questions in the question and answer box if you have any as we go through. So now it's my pleasure to introduce Dr. Sam Mason, Professor of Chemistry and Sustainability Coordinator at Penn State. Dr. Sherry A. Mason, AKA Sam, earned her bachelor's degree from the University of Texas at Austin. She completed her doctorate in chemistry at the University of Montana as a NASA Earth System Science Scholar. Her research group was among the first to study the prevalence and impacts of plastic pollution within freshwater ecosystems, focusing especially on the Great Lakes. While she continues her research endeavors, she has also recently moved into a new role as Sustainability Coordinator at Penn State Erie. Let me make sure I have this right. The BRAND College? BRAND? Did I get that?
Barron
I always
College.
make it harder than it is. Barron. Very good. So with that, Sam, feel free to share your screen and take it away.
All right. I'm here. Thank you all for being here and for the invitation to speak. I actually wanted to start with the preface that I am a chemist by training. The impacts of microplastic on human health is not actually my area of research, although I talk about it, obviously. So I study freshwater plastic pollution. And when I give public presentations, of course, the questions always come down, but what does this mean to me? Hence I got the invitation from Matt because he had been at one of those presentations. But I just want to clarify that this is not my area of research, but it is obviously because of my research. This is a topic that I'm very familiar. So when we're talking about the impact of plastic on human health, it's really kind of important to understand exactly kind of what plastic is. And the main component of plastic is a polymer. And these polymers come from fossil fuels. So when we talk about plastic pollution, kind of the impacts of plastic, we tend to focus on the pollution, the end of life of plastic. But really, when we're talking about human health impacts, this starts impacting human health all the way at the beginning of the life. And I think that this is very important to mention, especially with regard to environmental justice concerns. So this image and this next image here, these are taken from the largest petroleum refinery in the United States, the second largest in the world outside of Houston, along an area of the Gulf Coast that is affectionately referred to as Cancer Alley, because of the impacts that these refineries have on the communities that surround them. And of course, these are largely communities of color, and they have a very noticeable impact upon these people. So plastic is impacting human life at the very beginning because of that aspect. In my neck of the woods, I live in Pennsylvania. This is coming to hit home even closer because of hydrofracking. Which has led to, the Guardian to ask this question: will a push for plastics turn Appalachia into the next Cancer Alley? And the reason for this, I think when a lot of people think of hydrofracking, they think about the fact that it produces methane, natural gas, which is otherwise known as dry gas in the industry. But it also has the potential to produce wet gas. And here in the Marcellus Shale region, about half of the production leads to actually what is called wet gas. This is not very rich in methane and rather is very rich in ethane and propane, making it less useful as an energy source and instead very useful as for the production of plastics. So this image here is the it's taken from Beaver County, Pennsylvania, where they are building a ethylene cracker plant, as they are known. This will take this wet hydrofracked natural gas and turn it into polyethylene and polypropylene, aka plastic. And there are two sister facilities that are being planned for just over the Ohio border. So that after the one here in Pennsylvania gets built, two sister facilities are being planned. And this is why you have that Guardian article headline asking if we're going to turn into the next Cancer Alley. This is coming here because of the hydrofracking that happens, and these facilities end up producing these pellets that are then shipped and lost all along the pathway. So that's just the polymer. And we don't really know a whole lot about the impact of the polymer itself on human health. But in addition to the polymer, when we manufacture plastics, all sorts of chemicals are embedded within the plastic. These add certain properties. So plasticizers make plastics more moldable. UV stabilizers help them to be, more stable under sunlight. Colorants so that we can have plastic in every color of the rainbow. Flame retardants so that they don't spontaneously combust. And various other additives. So, and while these chemicals are mixed into the plastic, they are not chemically bound to the polymer. And as a result, they're well known to make their way out or leach out of the plastic into whatever is surrounding them. In addition, when plastic is out in the environment, they will absorb other chemicals, things like polyaromatic hydrocarbons, or polychlorinated bisphenols, will adhere to the outside of the plastics. Many of these chemicals are well known to be endocrine disruptors. What that means is that they mimic hormones of the body, and hormones are the chemical messengers of the body, right? So they transmit information from one part of the body to another part of the body. It's kind of like that game of telephone that we've all played in camp. When you start messing with those chemical messages, right, it can lead to a whole suite of human health impacts. From just to give you an idea of some of these known human health impacts that are attributed to these increases in endocrine disrupting chemicals in the environment, sperm counts are going down, as well as sperm motility. There's also impacts on women with regard to their reproductive health. Along the same note with regard to sperm counts, intergenerationally, penile size is getting smaller. That's the nice scientific way of saying it. Hopefully y'all can dissect that into what that means. This is real. This is true. Like we've seen this data has been recorded over decades and is being associated with these endocrine disrupting chemicals. In addition, certain types of cancer, this is kind of getting back to that Cancer Alley, right? But certain types of cancer are known to be associated with these endocrine disrupting chemicals. For women, breast cancer and ovarian cancer, and for men, prostate cancer. These are also associated with increases in autism and ADHD, as well as obesity. And when I talk about obesity, I'm specifically referring to studies that have looked at children under the age of 6 months. So this isn't, they ate too much McDonald's and didn't go to the gym. This is literally a reprogramming of our DNA to store more fat. And I understand that these things can sound rather incredulous, but there's actually a whole suite of books that have been written documenting this over the decades, the most recent of which is this book that just came out this year by Dr. Shauna Swan called Countdown: How Our Modern World is Threatening Sperm Counts, Altering Male and Female Reproductive Development, and Imperiling the Future of the Human Race. So this may sound, kind of quite dramatic, and it really is. If you haven't had a chance to read this book, I highly recommend it. And she has an entire chapter in this book, chapter 7, on plastics. So with that, I will thank you for your time, and I'm sure we'll get to questions at the end. So I will stop sharing my screen. and turn it over to the next speaker.
Okay, thanks, Sam. That was very informative. I continue to be, inspired and disturbed at the same time every time I hear you speak, but I really appreciate it. Okay, next, we're a little bit ahead of schedule here. So we have Dr. Chris Perkins from the Hampton Roads Sanitation District. Chris is an environmental scientist at HRSD in Southeast Virginia. He has been working in the water quality division there for 10 years on a variety of water quality related issues. Recently, he's worked on the SWIFT initiative, which is focused on microplastics and wastewater. I will let Chris describe what SWIFT stands for. So with that, Chris, please take it away. Chris, are you with us? Checking to see if. Fortunately, I don't see Chris as one of the looks like Chris is signed in as an attendee. Chris, it was a panelist link that was sent to you by Emily Montagna at Longwood University. Could you log off and sign on using that link, please, if you can hear me? And while we're waiting for Chris to do that, Rachel, why don't we go ahead and jump forward to you? Is that okay?
Yes.
Okay. All right. Thanks, Rachel. Let me just say a few nice things about Rachel. Rachel Miller is an expedition scientist, inventor, National Geographic Explorer, and Explorers Club Fellow protecting the ocean. She is founder of the Rosalia Project for a Clean Ocean and co-inventor of the Coreball, the world's first microfiber catching laundry ball. Rachel leads expeditions yielding results published in peer-reviewed journals and education programs that inspire thousands. She's presented worldwide, including TEDx and the Explorers Club. Rachel captains the 60-foot sailing research vessel, American Promise, certified hundreds of sailing instructors, trained Navy SEALs to use underwater robots, and mentors young scientists at the New York Harbor School. So with that, I'll let Rachel take it away. Thanks, Rachel.
Okay, great. Thank you for having me. You should see a picture of a really beautiful boat on the screen. And if no one's going to object, I am not on that boat. I am in Vermont right now, and we'll get rolling. First, I want to give you a little bit of background about who the we that I'm talking about is, and that is Rosalia Project for a Clean Ocean. Our mission is to clean and protect the ocean and conserve a healthy, thriving marine ecosystem. We address the problem using multiple angles of cleanup, always data with data cleanups. And then the rest is prevention through education, embracing innovation and technology, and doing solutions-based research. We address the whole water column, not just the shoreline, but the surface to the sea floor. That's our ROV, Hector the Collector, so we can get underwater without throwing anyone overboard. And we have been focusing on the land-sea interface at urban and coastal waters since the beginning. We thrive from really great partnerships with a lot of people, I'm sure, on this call. And we remain optimistic in the face of this overwhelming problem by recognizing that the collective we made it, and we think the collective we can help fix it, or can fix it. Lastly, we operate from a pretty spectacular research vessel when there's no global pandemics around, and I could talk about that a lot more, but we are talking more about solutions in this particular presentation, and we think about that a lot, is how does our work relate to solutions and even the big picture of what it takes to go from a problem, finding out about a problem, to helping make it stop, whether that's prevention or cleanup or a big combination of all of that, which it usually is. And so this is our kind of working graph of, or flow chart of solutions. And for Rosalia Project, we exist really primarily first and foremost in the front end of believing that you can't solve problems that you don't understand. You don't have to understand every single thing to get started, but our expertise is in field science And we have great respect for and partnerships with people on the lab side of things, but we're expedition science group. We then spend a lot of our time on the solutions side in education and awareness and in working on innovation and redesign with our best efforts to provide data or anything we can be helpful for those who have expertise in working on policy and regulation, as well as in infrastructure and even using financial instruments to address the problem of marine debris in all of its sizes. Okay, so as far as Rosalia Project goes, we do work on 3 of the marine debris problems: derelict fishing gear, consumer debris, and microplastics, which brings us to why we're here today. This audience doesn't need to be introduced to the problem of microfiber pollution, but I'm curious if any of you have seen essentially what sets it up. And the microfiber pollution I'm talking about is that caused by fiber fragmentation from our textiles, our garments, our home textiles, but primarily we think our garments. This is the part of the problem that we've been working on. So what you're looking at right now are magnified images of some pretty frequently found textiles in our world. So you can see they're labeled there: acrylic going along the top, 2 different kinds of polyester, woven and non-woven, cotton poly blend. I always like people to try to guess this one on the bottom left. I think it's fascinating and beautiful to look at. We've got some nylon spandex, linen and rayon, and 100% cotton. And the reason I like to share these is to not vilify our clothing, but to demonstrate its potential fragility. And that a lot of what makes clothing what it is. And so sometimes that's soft and lovely. And sometimes that's repelling all water or keeping us cool or keeping us warm. It can set up a situation that allows for fiber fragmentation to happen easier. And if anyone was guessing, that bottom left, that is the nylon layer of a black wetsuit. I think it's quite beautiful. So when we learned about the microfiber pollution, it was around 2013. We did not discover it. That happened from at Plymouth University, but we heard about it pretty early, and this was a problem that screamed at us. And so we set about to try to accomplish 3 things. We had 3 goals when we learned about it. One was that we wanted to see if we could come up with a solution and stop it ASAP, as soon as we could. We wanted to raise awareness and inspire people in the myriad industries in which we have no expertise, upstream of people and downstream of consumers, to learn about the problem and see what they could come up with. And finally, to contribute to the, at the time, scant scientific knowledge about the problem of microfiber pollution in particular. And this was microfiber, not just the plastic, but also the non-synthetic bits of our clothing. So one of the questions that we set out to answer was, well, what does this look like in the wild? So here's some microfiber that we got from the wild. We did that by sampling the entire Hudson River every 3 miles from Lake Tier of the Clouds to Ambrose Light. I expected a very clear increase in fiber around the people, like between Manhattan and New Jersey, where there are a lot of people, a lot of wastewater treatment plant gallon outflow, but that's not what we found. In fact, what we found was this kind of fascinating twofold situation. One was the place where we found the most microfiber was next to a wastewater treatment plant, but otherwise no statistically significant difference in microfiber across the whole river. Now, our hotspots were also surprising. Besides the one next to the wastewater treatment plant, they were even above wastewater treatment entirely, these 2 on top. Total alpine, no one's allowed to live near there type of locations. But we weren't the only ones to find that kind of a pattern. A friend and colleague, Kirsten Kapp, looked at the Snake River same year in a similar way. Longer river, so rather than every 3 miles, she did every 100 miles, but it was 3 times the length. And she found her hotspots to be similarly unexpected. And so as what happens with science, when you kind of look at this, wastewater treatment plant was the biggest. So it's not about washing machines and wastewater treatment plants. However, it can't just be about that because of how much we found where there are no municipal wastewater treatment plant outflows means that there had to have been other sources. And so the stuff that we thought about was along the lines of atmospheric deposition, runoff, and then specific sources like dryers, alpine recreation, just wearing our clothes and having the stuff fly around. And so as happens with science, that spurred 2 studies. I'll do the one that we executed first. And and just real quick before I go into that, on the dryer side, this was in October 2016 when we got our data that said this isn't just about washing machines, is I went outside and this was outside our dryer vent, basically foliage covered in microfiber. At any rate, that underscored and sort of set us off in this direction to go back and collect more information. So in 2019, we went back to the Hudson River. Again, every 3 miles from the mountains to the sea, but this time more than just the surface samples, we took air samples. So when we were on American Promise, which was from Ambrose to Albany, we did 2, one high up the mast and one at my inhalation height. The my inhalation height was the same throughout the whole river. We took 3 soil samples where there was actually soil, so not many in Manhattan. We took the surface samples again, mid-water column and a meter above the river bottom. And also we took some very small amounts of water from the sample for a look at nanoplastic. Just so I can share the breadth of the expedition, we also did a couple other studies within the big one. This was to look at wastewater treatment plant outflow at a rural, a suburban, and an urban location. And we took 27 samples to make a cross section and always at the same state of tide. We're still waiting for these data we're getting there. We also supported some really interesting science enabling innovation that included easy lift tape. There's now a paper out about that from our partners at Staffordshire University and Dr. Claire Gwinnett. It's pretty amazing. If you've had to do vacuum filtration before, you'll find that this is a huge enabler for a lot. And also looking at another partner from Ocean Diagnostics, an in situ microplastic sampler that helps take away all the dangers of contamination. Finally, we also did some videoing to see if we could contribute to some AI and auto identification of marine debris. So back to, all right, now as far as that goes, I'm going to share some data in a second from that, and we're still working on it. So we'll keep in touch about the results from those studies, and we're excited. We had COVID get between us and the lab, so we're getting there. So back to the dryer. Now, this is what things looked like another year later when we got a new dryer. And when we magnified the stuff that was coming out the dryer onto our beautiful flowers, it looked exactly like what we find in the washer when we drain washer effluent. It's really the same stuff. And so my friend and colleague, Kirsten Kapp, and I set about it last year to really understand what are the emissions that dryers are putting into the environment. We realized snow would be a great enabler to make this science run smoother. And so we used a bright pink blanket that also helped things. And we looked at what happens when you wet and then dry a blanket and let it go. And so what we found wasn't surprising on one level. And I'm just going to go to the next slide. It's a little bit easier to read. Here's the heat map at my place. We had 2 different locations, one in Idaho and me in Vermont. And so the bigger or the redder the circle, bigger and redder the circle, the more fibers fell right there. So 5 feet from the vent, we obviously saw the most. But we did a semicircle at the 30-foot range and saw a surprising amount of fibers fall 30 feet away. So this is really making its way much further than just the bushes under one's dryer vent. And so that prompted us to also want to know, well, what's getting out completely? And so we did that by capturing everything in a bag. Top layer is the location 1, bottom is location 2. So interestingly, you saw a really big difference between the 2 locations, not just in what was emitted by the dryer out to the world, but also what was caught in the lint traps. And there was also a pretty big difference in lint trap sizes. So we get some really interesting information. The paper is in open access and I can share it, or just look up Cap Miller and +1. But, we're thinking a lot about this. Well, okay, so now what? Now we know that dryers are also a direct emitter of microfiber pollution. What can we do about it? So our immediate conclusion is to do less laundry, which is the same advice that we give for washing machines. Air dry when possible, but we've got to learn more and definitely keep those lint traps clean, not just for reducing fire hazards. And for those of you that have students, are students, or about to become a student and need some capstone project topics, we have a whole list of research that could really be translated directly into action. So please keep in touch on that. Now, that second study that or the first study to come out of the Hudson River expedition that we submitted. So please do not tweet this. This is preliminary, not ready for mass sharing yet, but I'm sharing with you guys because it's pretty surprising. One of the bits of work that we did on the Hudson was to test all of the protocols that we were using. We were so careful about reducing contamination from our own clothes, that of the researchers and the boat crew, the boat itself, and very consistent about it, using the state-of-the-art forensic techniques. And we wanted to know, does that matter? Not just for ourselves, but also for thinking about citizen science and for microfibers in particular. And so we looked at the effect the protocols had and the effect that removing the protocols had. And the way we knew what was contamination is we took scrapings from every garment, every textile, every piece of rope, every sail bag that could have possibly contributed. So all known textiles. And when we found a fiber in an environmental sample, we first compared it to these known objects or these known garments and textiles. And so we were able to see something that surprised even me. And that was that when we used all the protocols, 33.7% of the environmental sample was from known sources of contamination, mostly the clothing worn by the field sampling and the processing group, which is pretty crazy. But then we said, all right, when we took away the protocols on deck, so this is sort of the equivalent to the field, what happened? And the amount of contamination in the environmental sample went up to over 70%. When we did it all perfectly on deck and we took away the protocols down below in the galley, where the lab was, we were just below 70%. So my conclusion there is that we are all pigpen. Instead of poofing out little bits of dirt, we are poofing out little bits of fiber from our clothing. And this is a tough one because this is kind of how everything was laid out. We did the sampling on the bow, always pointed into the wind. We did the processing down below. Nobody was allowed to go through there if you weren't directly involved. And the boat ops team never came out of the cockpit. And yet we found fibers from our captain's surf shorts in the samples. It was crazy. So I don't have a lot of solutions yet for this other than to understand more. And again, to make an appeal for the research community to understand more about what causes or reduces resiliency in our clothing. Now, in terms of the washing machine, and one of our original goals after learning about microfiber pollution in the first place, I introduce you, if you haven't already met, to the Coreball. Coreball is a consumer solution. It goes in your washing machine, and it's that easy. It works in any washing machine at all. And the very shape and function of it was inspired by coral itself, because we realized that coral catches small things from moving water, and that's what we needed to have happen. So here's what it looks like in a washing machine. It moves with, not against your clothing. And here's what it looks like when you get fuzzballs. There's a fuzzball. To your naked eye, it looks like hair, but we're going to put this under a digital microscope, and you'll see what we see is just, it looks like a hairball, but what it is really is a little bit of hair. That's the big thick bits, but also a lot of pieces of microfiber. I mean, this stuff is small, and the Coreball tangles it up. No, this is what all those bits of fiber were contained in that little fuzzball. The Coreball helps people be part of the solution. It is not the solution, but it is certainly part. And we've had some independent tests that have shown we're up to about a third of reducing the shedding, or that catching microfiber that would otherwise wash out the drain, but it also helps reduce shedding in the first place. And you have to imagine that we're psyched about that. So in terms of washer emissions, it's not just about the Coreball for solutions. There are a lot of actions that people can take that don't involve anything other than a little bit of behavior change. So I have some of those listed here. And one of those, you might have seen some of these already before. Asking companies for inline filters for me is about communicating to washing machine companies. Most of the communication has been to clothing companies. And my experience going to a lot of these multi-stakeholder meetings is that companies respond, especially to kind of respectful, knowledgeable requests that just say, hey, I love your washing machine, but the one I've got, which is pretty much everyone's right now, especially in the US, isn't catching microfiber. I would like that to stop. I will buy my next machine from you if it's got that. So just something to think about there. And again, more research. In particular, I would love to see some research related to septic tanks and leach fields. And as always, understanding textiles. So the last bits of action that we're taking from a solutions point of view has to do with translating our expedition science and our activities that we're doing in innovation into education programs, and to show people that inventors are not just 30-something-year-old dudes from San Francisco, but they can be you, they can be anyone. So we've got microplastic education programs. We bring people, show kids how we're doing the actual science, but not just as a demonstration, but like, here, get your hands on the Niskin bottle. This is how it works. And also doing some really fun, you can do this at home. We actually have the curriculum available to run some really fun microfiber activities. Again, you can just do it at home without even specialized equipment. And finally, recognizing the importance of what National Geographic calls science telling. If there was ever a time to have people communicate clearly, enthusiastically, and in robust ways about science, I would say now is the time. And so we're working on that with the people with whom we teach and present. So to really wrap up, I want to just leave some thoughts. This is how we think about microfiber in particular and opportunities to solve the problem at the multiple places, looking at circular economy. The first step in that is to prevent the problem from happening in the first place. And knowing what we know about our contamination study, that's got to be in understanding what makes our clothing more or less resilient and figuring out ways to make it more resilient. In terms of stopping the leakage, that next part to say, okay, well, we probably can't make our clothes never break. So a little bit's going to break. And we're going to have those little bits of fragmentation. So now we got to stop it. We got to keep it from getting to our public waterways. So that happens, we hope, in washing machine filters. So less to think about. Also reduce dryer emissions. Now that we've done that study and understand the magnitude of that part of the problem, that really hasn't been part of the conversation, that's got to be now part of the conversation. Same companies making both items. And then of course, consumer actions like the Coreball. And then closing, and of course, wastewater treatment. I made them smaller because I feel like we need to lean on them less. But I think our next speaker is going to talk about that, which I'm psyched about. And then finally, closing the loop. What can we do with the laundry lint? So now we're not just catching dryer lint, we're catching washing lint. What can we do with that? And can we do something useful in an upcycling sense Because if we can figure that out, we can also solve some of the other problems facing our fashion industry, which is, what do you do with mixed garments, mixed material garments? So it's a real technical challenge to take a tangle of cotton, rayon, PET, recycled PET, polyester, all this stuff all mangled up together. It's a real challenge. So one that I think can be solved. And I appreciate getting to share all this with all of you. If anyone would like a follow-up on anything I talked about, or to join us on American Promise in the future, here are my contact details. And we'll move on. Thank you.
Thank you so much, Rachel. That was great. And I believe these presentations will be posted to the Marco website, so folks can get your contact information from there as well. And feel free to put that in the Q&A for everyone to see. So thanks again. Next, we have Chris Perkins. So
right,
Chris, I already gave your bio, but I'll just say one more time that you're with the Hampton Roads Sanitation District, and that you are working on the SWIFT initiative, which is focused on microplastics and wastewater. So I will turn it over to you now. Thank you.
All right, can everybody see everything? Can everybody hear everything?
Yes.
Oh, okay, good. So let me pull my presentation back up. You should be seeing my cover slide, microplastics and wastewater treatment. I gave a similar presentation to the 2019 Microplastic Stack Conference. Just want to kind of go through a little bit of work that Hampton HRSD has been doing on microplastics.
Hang on, Chris. We don't see your presentation. Did you share your screen?
Let's see. I thought I did. Share screen. Yes. Sorry about that.
No problem.
You would think after 18 months I would be proficient at this.
We all are there with you, man. So no worries. Thank you so much. I can see it now. Thanks.
Okay. All right. So anyway, this project was driven by SWIFT, and that's a Sustainable Water Initiative for Tomorrow. But the emphasis wasn't on microplastics. Microplastics was an inadvertent consequence of it, and I'll get into that as we move along. First, a little bit of background on microplastics. Microplastics were first reported in the 1970s by Carpenter et al. They were doing some work in coastal Atlantic, and they were finding polystyrene spheres. And this drew pretty minimal attention from the scientific community. And then in, I guess it was 2001, Moore et al. Published an article documenting pretty high incidence of plastic debris in the North Pacific Gyre. And this was part of the JGOFS program. Interest since 2010 has culminated in microplastics being listed as a high priority research area. I went through and did, sort of some Google Scholar statistics. 2010, the number of articles that had the word microplastic in it were pretty minimal. And that goes up through 2019, where there was over 1,000 articles with the word microplastic in it. You can see sort of a visual description of that from Web of Science. So why are we concerned about microplastics? Microplastics lead to biofouling of organisms, shellfish, things like that, small fish fry. They lead to entanglement of marine and aquatic organisms, but also they're concerning because of potential toxicity issues with additives to these particles. And some of these toxicity issues, coupled with some biofouling concerns, can lead to growth and reproduction issues in aquatic organisms. Microplastics, I feel like we really need to make sure we have a description of what a microplastic is. This is from UL 2015. They break it down into different sizes, greater than 5,000 microns, 5,000 to 1,000, 1,000 to 0.1, and then a new criteria that we're starting to look into are nanoplastics, which are less than 0.1 microns. Types of plastics being broken down into primary and secondary products. And then also the fibers or fragments, films, beads, and foams. And then lastly, the composition, or what types of chemical compositions of microplastics are we seeing? Polyethylene, we've talked about this. And then also sources. Where are these microplastics coming from? So this was from a study from the European Union. I thought it gave a good description of the different sources of microplastics. I'm not saying that the weight of these sources is accurate, but wear and tear from car tires was a source, painting and maintenance of boats, the plastic production process, painting and maintenance of building and construction along roads, washing of textiles, wastewater treatment, illegal dumping of paint, indoor dust, and microplastic additives to products. And then lastly, cosmetics. You can kind of see from this figure how they sort of modeled how these microplastics move through different through the marine environment. Getting a little closer to home, so the Chesapeake Bay wastewater treatment plants. Here's sort of a graphical description of the Chesapeake Bay watershed and where specific wastewater treatment plants are. What I really wanted to get at is, things tend to be focused along the Chesapeake Bay, but also that the sheer magnitude of wastewater treatment plants in the watershed. There are almost 500 wastewater treatment plants. This was from 2009. I would guarantee that there have been additional treatment plants constructed. They treat on average of 1,600 million gallons. So that would be, 1,600 MGD during dry weather and 3,500 MGD during wet weather. So the difference is some wastewater treatment plants are called combined sewers. HRSD, we don't have combined sewers, but DC Water, for instance, is a combined sewer treatment plant. And that means that they collect both sewage and stormwater runoff. So there's some serious design considerations that have to be taken when you operate a treatment plant like that. HRSD, we're focused strictly in Southeast Virginia. We were created in 1940. We're a political subdivision of the Commonwealth of Virginia. We were mandated because of shellfish ground pollution in the 1930s or so. We treat 1.7 million people, or we have 1.7 million people in our collection area. We cover approximately 3,000 square miles. We have over 500 miles of piping to move sewage to one of 17 different treatment plants. Actually, we picked up a new treatment plant. We're now in the process of taking over a plant in Onancock. The locality is giving up the plant, and the state has asked us to move in and take over operational control. So of these plants, we have all shapes, sizes, and volumes that we treat. No two treatment plants are ever the same. We have 9 major plants that are operate in the range of 15 to 54 million gallons per day. These plants all have secondary plus enhanced biological nutrient removal. And this is because of the Chesapeake Bay Act and nutrient removal requirements that we have to meet. We also have minor plants, and these tend to be small community plants that operate, anywhere from 25,000 to 600,000 gallons per day. But these also have to meet very stringent nutrient removal requirements for nitrogen and phosphorus. A little bit about nutrient removal. You heard me say earlier, no two treatment plants are the same. Depending on what type of treatment plant you're operating, you may operate under a secondary treatment process where you're removing total nitrogen, or you're doing primary and secondary removal. There's enhanced nutrient removal where you're actually finally starting to drop the nitrogen down and remove nitrogen. However, this process may or may not include phosphorus removal. And then the way that HRSD is operating their facilities, we're doing enhanced nutrient removal plus tertiary filtration. And this means that we're doing biological nitrogen and phosphorus removal, but we're also doing very stringent particle removal. And these are through things like sand filtration and things like that. Now I should clarify, the particle removal, this is sort of an inadvertent issue related to some of the different nutrient removal technologies we're using. Some of the bacteria, they're not free floating. They have to actually stick to particles. And inadvertently, this sand obviously removes a lot of the microplastic particles. Now we'll move on to a case study, the Nansman wastewater treatment plant. Any of you guys familiar with the Hampton Roads area? This is on the south side of the Monitor Merrimack along the James River. It's a 30 MGD facility, typically operates between 15 and 18 MGD per year. We operate a secondary treatment system with a 5-stage Barden flow, and we also do full biological phosphorus removal. The VIPDES permit, we get an acute dilution in the James River of 73:1 and a chronic dilution of 600:1. This is important. I'll tell you later on when we do some back of the envelope calculations. The treatment plant receives 80% domestic wastewater, which comes to about 198,000 homes, and about 20% industrial wastewater. Now, this facility, we've also built a SWIFT research facility. The SWIFT research facility is basically where we've taken drinking water, we've stuck drinking water technology onto the end of our wastewater treatment plants. And I'll kind of go through that. Oh, first we'll do it, just kind of show you how the Nansman treatment plant is set up. So raw influent comes into the plant. There's also a point for septage and grease. These are from your sort of like your fats, oils, greases from restaurants and things like that. It goes through a bar screen, which captures large solid particles. But, you know, we get lots in regards to microplastics. It comes to things like, you know, candy bar wrappers, Q-tips, straws, things like that. Then it goes into grit removal, which is where a lot of the sand drops out, but also a lot of the high density plastics. And then finally into the primary clarifier. Primary clarifier is where all floatables and sinkables drop out. It goes to aeration, which is where nutrient removal happens. Then finally to the secondary clarifiers, and this is where we recycle our heterotrophic bacteria, but we're also wasting some of these bacteria. This is called WAS. And so we get a lot of microplastic removal here. Now, prior to SWIFT, everything from the secondary clarifiers would be discharged into the James River. But because of SWIFT, we're actually going to start diverting 80% of the total flow from this plant into this SWIFT treatment process. So we're effectively removing 80% of our yearly flow and sending it into this advanced treatment process. So the next slide is going to look at what that process involves. So the SWIFT process, you can see the secondary clarifiers, we're pulling water off of those, and it's going into a rapid floc-sed treatment process. So we get a lot of microplastic removal here. And these I should mention that these are all mostly fibers at this point. Goes through ozone. This ozone contact system is basically really meant to chop up a lot of the organic molecules. The residence time there is not long enough to have any effect on plastic particles. But the next step are these giant activated carbon biofilters. And these biofilters act as sort of a physical filtration mechanism for removing plastics. And from there, it goes to a granular activated carbon filter column, which also functions as a physical microplastic removal. From there, it goes to UV and then a chlorine contact, because this water then gets injected into a deep confined aquifer. So we worked with VIMS, BK Song and Sam Fortin. We sampled throughout the SWIFT process, and we counted and identified microplastic particles using Raman spectroscopy. This is their setup. I won't go into too much detail about it, but basically what we did was we filtered the wastewater or the water samples from the SWIFT process using a 5-micron filter, and we digested the material that was captured on that filter, resuspended it, quantified it, and identified the plastic types. And this is an example of a polyethylene particle that we identified. So we were only identifying particles greater than 5 microns. That's an important note. So anyway, back of the envelope calculations. The SWIFT feed from the secondary clarifiers was around 32,000 particles per liter. The post-floc sed, so the material leaving the floc sed, was decreased down to 3,000 particles per liter. The BAC, the biological activated carbon filter, it went up to 4,000 particles per liter. This may have been just a noise issue or contamination. Contamination is a big concern here. And then the post-GAC was down to 900 particles per liter. So going through these different chemical and physical filtering processes, we are removing microplastics inadvertently. Just to kind of go back and compare what would happen during a normal operating condition, where the material from the secondary clarifiers was at 32,000 particles per liter. So the plant is kind of like right here. And you can see here, this is where the outfall is, where this green dot is. These are the VDH shellfish condemnation zones. But you can see here the acute dilution, which was, I want to say it was like 73:1. That dilution factor would drop this down to 400 particles per liter, and then the chronic dilution zone would further dilute that down to 50 particles per liter. So obviously this doesn't do anything for particles that are floating, but for high density particles, we felt that this was advantageous for shellfish, in the once you leave the condemnation zones. So in conclusion, we do feel that microplastics are a significant pollutant. We do think that better analytical methods are needed to include standard methods, sample contamination control, sample ID and enumeration QA/QC. We also need to understand some of the other sources. There's, highway stormwater runoff, stormwater BMPs, marinas. We see a lot of plastic pollution from marinas. We also need to start to think about understanding microplastic toxicity properties. And then lastly, as a wastewater person, we do feel that the dilution zone precautions do provide significant reduction in microplastic encounters with, I said pelagic, but I feel like this is probably more so with benthic aquatic biota. And let's see. Oh, and this is a picture from Portsmouth, Virginia, prior to our creation, where raw sewage was basically running from homes through ditches. You can see the kids playing there. And just remember that we clean the wastewater that the public creates, and in an effort to try and protect public health in the waters of Hampton Roads. And our mission statement, this is a picture of a diffuser going into the York River, and my contact information. And so that's pretty much all I've got. So I will, let's see, how do I do this? Stop sharing.
All right, Chris, thank you so much. That was great, very interesting. Now, at this moment, we will be asking for all speakers to put their cameras on as we have a panel discussion. So please don't be shy. We will be asking questions that you have been sent, in from the registration form, and if time allows, we can raise questions from the audience. Please use the Q&A box, not the chat box, to add in your questions, thoughts. I'm going to break the rules for a second here, Chris, and just go back to your presentation, if that's okay. I believe when you and I previously spoke, you mentioned that once SWIFT is fully implemented, and maybe you can elaborate more on the timeline for that, you're expecting to see your effluent from all of your sewage treatment plants to the Chesapeake reduced by 80%. Is that correct?
That's correct. We're going to reduce our total. Now, we can't do it for all of our plants because of the, there's a meteorite impact crater in the lower Chesapeake Bay.
Exactly. Yeah. Yeah.
And so the stratified, I'm not a geologist, but you know, the stratified layers don't allow us to inject into a confined aquifer for some of our plants. So it's only the plants along the James River and then one on the York River.
Okay. So not all of your plants, just those particular plants you'll be reducing 80% of your effluent from.
We estimate that our total reduction, our typical flow is around 150 million gallons per year or per day. And that's going to drop to about 20 to 30 million gallons a day.
For just those plants, or the
our total flow will decrease to 20% of our current flow.
Wow, that's a big deal.
So it's having some unintended consequences, or not consequences, but impacts, because we're also reducing some of the, so I'm a toxicologist doing a lot of work on PCBs as well. And so we're getting ready the James River is getting ready to get a TMDL for PCBs. And, you know, that 80% reduction is huge as far as the total PCB load coming from wastewater treatment plants. So the same is true for microplastics as well.
Really impressive, very impressive stuff. Okay, well, now we're going to go back to the questions that were what we call them pre-questions that were offered up during the registration process. I think this first question is for all the panelists. Are there some types of microplastics, microfibers, more of a problem than others? And feel free to speak up. Anybody? Bueller?
Go ahead, Rachel, you go first.
Oh, I was just going to say, you know, for us, we don't want any of our man-made things in the bellies or anywhere in fish. And so we did design the Coreball very deliberately to be an equal opportunity fiber catcher. We wanted to stop it all. There are physical and chemical components that make up the list of dangers that microfibers pose to creatures. And it appears that on the physical side, that all microfibers, whatever their original generation, whether that's non-synthetic or synthetic, they seem to all be implicated. So we can't say that a cotton microfiber is harmless. I don't think that's accurate at this point. So that's one of the reasons. If you pressed me, I would say I would be working a little harder on the synthetic side because of the additional potential complications and what Dr. Mason had to say. That's sobering on any level. So yeah, so go ahead, Sherry.
Yes, I was going to say that I think microfibers are a bigger issue than other types of microplastics. From the literature that we see with regard to wildlife. In most, when we're talking about microplastics, so I think a lot of times when we think of impacts on wildlife, we have those images from Chris Jordan with albatross and, you know, cigarette lighters and toothbrushes in their gut, or the washed up whale filled with, you know, 40 plastic bags. So that's macro debris. But with regard to micro debris, especially within freshwater and these kind of estuaries, it tends to be, the impacts on wildlife tends to be mostly focused on microplastics as opposed to macro, and microfibers are the most prominent. So I can tell you up here in the Great Lakes, with the exception of oysters, every other species that's been looked at, it's always microfibers. In our own studies of fish, it seems that, beads and fragments tend to be not only ingested, but egested. But microfibers tend to become basically enmeshed within the gastrointestinal tract and really become part of the organism. And the longer that plastic is within the organism, the greater potential for those chemicals that we are talking about to leach out. So I put microfibers as being kind of the kind of biggest concern when it comes to microplastics. But all microplastics are of a concern, right, to some extent.
So on that note, Sam, and this kind of gets at our second question, and I know Rachel touched on that they're actually looking for nanoplastics as part of the Rosalia project. A nanoplastic, a nanoparticle, for those on the phone, just to provide some perspective, is 1/1000th in length or diameter of a particle that is 1 millimeter in length or diameter. It's extremely, extremely small. And correct me if I'm wrong, but we are having a hard time figuring out ways to actually detect and analyze for nanoplastics. Do you think it's potential, there is potential for nanoplastics? I know what you're seeing now at a certain size level is microfibers. Do you think there's potential for nanoplastics to be playing a bigger part in this and potentially causing severe human or even ecosystem health effects?
Oh, absolutely. Any particle that's smaller than 100 microns can make its way across the gastrointestinal tract. There's a really extraordinary and depressing study that came out, I think it was just earlier this year, looking at the placental boundary and found microplastics on both sides of the placental boundary. I think it was around 20 microns, so we're still not even down in the nanoparticle range, but 20 microns are smaller. These are definitely making their way across the placental boundary, across the blood-brain barrier boundary, and so they are making their way into our livers, our kidneys, our brains, all of our organs. And what is the potential impact of that? That's really kind of the forefront of the research. But there's no doubt that as the particles get smaller, the concern is greater. When I first got into this area a decade ago and I would give talks, I would talk about how I know the aesthetics of big pieces of plastic are disconcerting, but it's the smaller pieces, it's the pieces you can't see, those are the real concern. And the smaller we go, the greater the increased risk.
So, we're very interested in the Chesapeake region because we've developed a science strategy, as Bob talked about, which includes monitoring. Rachel, could you talk a little bit more about nanoplastics and what you guys are doing to monitor for them as part of the Rosalia project?
Yeah, I'm afraid that we don't have an actual nanoplastic program rolling yet. The company with whom we were working for nanoplastic sampling on the expedition in 2019 was Luminex, and they worked on COVID stuff. So we're still waiting for a little connection there. I will keep you informed though. It will be very interesting. Obviously, we have a hypothesis that the patterns will be similar, but it'll be fascinating to see what the concentrations are. Got
it. I guess this is open for everybody. What are practical solutions that anyone can do to combat microplastics? For example, are there steps that residents can take to prevent microplastics from entering the waste stream from homes? And Rachel already touched on that with Coreball. We looked at what we're doing at the end of the pipe at wastewater treatment plants. Are there other things that we could be doing to impact this?
The biggest thing to do is to stop using plastic. I mean, that's like the most basic thing. And so it's bringing your reusable bags to the grocery store. It's using, you can't see my mug. It's using reusable cups, straws, takeout containers. And there's so many options out there. So it's making use of those options. And, you just go one item at a time, you know, and just start making changes. I changed my cleaning products. I changed my toothpaste. I changed my toothbrush. I changed my bags, my bottles, my straws, you know, my laundry detergent, you know, all of it, my laundry, you know, dryer sheets. I use, you know, wool balls and scents, and I get those in class, you know, I mean, there's just so many options out there, and you just got to go one option at a time through your house. You know, keep track of the plastic items that you use and find alternatives.
You know, I totally agree with you, Sam. And I think we've been lulled over the last 30 years or so into a false sense of plastic management by having recycling programs everywhere. And so, yeah, the whole idea is like, oh, we're closing the loop. That doesn't do it. You know, you have to actually remove the consumption of plastics to begin with. Completely agree with you.
If you saw the tons of plastic that come into wastewater treatment plants in the form of Q-tip, you know, personal hygiene products and things like that, it is unbelievable. I mean, the number of dumpsters fulls of material that we send to, you know, landfills that are just plastics. I mean, it shocks me the things that people think you can flush down the toilet. So
dog poop bags. If you're gonna pick up your dog poop in plastic, please take it to a trash can. I'm in the process of, y'all were talking, Bob, I think, was presenting the litter booms, right? We have a litter boom. We have 2 here in Erie, and we're doing a study on what is caught behind those litter booms. And I cannot tell you how many dog poop bags make their way down storm drains and end up, and then we're fishing them out. And, you know, if you're going to pick up your dog poop in plastic, throw it out, get rid of it, you know. And I've walked in the middle of a forest and found dog poop bags. I was literally in the Grand Escalante in Utah in May and found two dog poop bags in the middle of frickin' Grand Escalante. Ah! Okay, I'm going to stop.
Okay. Well,
I saw that there was a question about biosolids from Rob Hale.
sure, go for it.
So Rob and I are actually working together on, so biosolids, let me back up. So we're talking about, you know, wastewater treatment plants and, you know, removal of microplastics. And remember I talked about the waste activated sludge. And so there's a significant amount of plastics that get trapped in that material. And so a lot of that material, depending on the treatment plant and the purity of it, you know, it gets land applied. And so this land application of biosolids is another potential source of microplastics into the terrestrial environment. We're kind of concerned about it because of the potential toxicity issues related to these microplastic fibers. You know, it's used in agricultural settings as mostly a phosphorus source. So, you know, that's just another pathway for these particles to move into the environment. So we don't know the magnitude of biosolid microplastics at all. Now, fortunately, a lot of treatment plants they're not allowed to land apply because of, you know, organic pollutants, metal pollutants, and things like that. They're very strict rules about land application in regards to that. But, you know, we do a lot of land application from one of our plants. DC Water does land applications. You know, the biosolid program is pretty big in the Chesapeake Bay area.
Chris, is that where all of the microplastics that are taken out at all the various places, do they all end up in that, or do some go to landfill?
No, most of the material goes to the landfill. The material that comes into the plant first gets caught in the bar screens. That's a very coarse filter. It gets the big stuff. And then the primary clarifiers is where the majority of the smaller particles are going to leave the system at. They're either float to the surface or sink to the bottom, and then they get physically removed.
And they're part of the landfill bound?
That's part of the landfill. So the biosolids are strictly the heterotrophic bacteria that are being wasted from our treatment process. You know, you can think of it as sort of a bacterial culture that's growing exponentially, and we have to keep it at a certain biomass. So we're constantly wasting some of that microbial culture, and they're plastics that get trapped in that material.
Yeah, I appreciate that. And it is definitely a place where there needs to be more information. It's also, I also appreciate that it's a helpful way to respond to one or two of the questions just about, okay, so if you can trap or if you can catch your washing machine lint, people, it feels hard for people then to throw it in the trash. But our kind of thoughts on that are that stopping it at the household level and putting it in the trash is removing some of the unknown potential for it making its way into the public waterway, because the places it goes, if it gets to wastewater treatment, are potentially the river, but also more likely either land applied or landfilled anyway. But no, it's actually why we put wastewater treatment as sort of one of the smaller solutions. We don't want to put it all on you guys.
Well, you know, it's also important to consider. We do source control for organic chemicals, or a lot of organic chemicals, because it's easier to treat it at the source than to try and pull it out during the 18 hours that a body of water is moving through our plant. And so I feel the same is true for microplastics. We have a huge problem with pharmaceuticals. I won't even go into that today.
We want you to spend your time on that.
So just the number of pharmaceuticals that we see coming into our plants is unbelievable.
Yeah. No, I appreciate that. So yeah, that's what we're working hard to solve this problem at a higher percentage upstream of you.
So since we're talking about monitoring a little bit, and you know, in this region we have a science strategy now. What are your thoughts on citizen science opportunities, either for collecting microplastic data or for cleaning them up?
I mean, from my standpoint, the cleaning up, I am not a proponent of like the throwing the baby out with the bathwater. I don't think vacuuming or doing wholesale slurping of all the algae, all the good stuff, with the small stuff. And if there's any good stuff that's bigger than the small stuff, then we have a problem with cleanup. And therein lies the problem with cleanup of something. I mean, microplastics themselves, but microfiber is another step more difficult. So for us and our energy and focus, it is entirely on that kind of prevention, make clothes more resilient, stop it before it escapes, and the bits that we can divert before it escapes, give them some useful life, because that is a really, really hard one.
Absolutely. The only solutions, right, are the most upstream. That's how you really solve a problem. Citizen science is great for we need more data. There's not enough of us doing this work, honestly. You know, I think y'all pointed out early in Matt and Bob, early in the conversation about how little data there was on the Chesapeake Bay. Well, you're starting to get data now, but that's true for like every body of water out there. You know, I mean, there's just so little data because there's just not enough of us doing this work. I mean, Rachel, when you're talking about all of these, you know, experiments that could be done, it's like, yes, we all have this list and we don't have enough bodies. You know, and I work in higher education and we don't have enough bodies doing this stuff. So it's great for getting data. It's always, you know, going to be somewhat limited, but that's fine. You know, you know what those caveats are. It's also really important because getting the people out to do cleanups, they're not going to be probably clean up microplastics, but bigger pieces of plastic, meso and macro. It really helps people to understand the scale of the problem. I love taking students out to a relatively pristine beach and they go, this isn't bad, we'll do a cleanup. And an hour later, we've got 300 pounds of stuff. And they're just like, oh my God, you know. And it really kind of hits home. And it's always the odd things, you know, I have them pick out their favorite, like weird thing, and it'll be like, you know, part of a fan, or, you know, of course, the beach whistles. If y'all know what those are. Tampon applicators, they're oftentimes referred to as beach whistles. So yeah, things like that, that people don't expect to see. And then they start kind of having a greater awareness as to the scale of the problem that we're talking about.
And
I will say there have been some solutions in this region that have been inspired by citizen science data collected, specifically in Virginia, when they found that the shotgun wads were most common along beaches. I know Katie and Laura worked on this extensively, and the VIMS folks worked with them. For those of you who don't know what VIMS stands for, Virginia Institute of Marine Science, to come up with a bioplastic to replace the material collected by shotgun wads. To replace the material used by typical shotgun wads, which were plastic. And we do collect a lot of citizen science data in the district, specifically from cleanups, keeping track of how many plastic bags we see during cleanups. The straw ban that we now have was inspired by citizen science data collected during cleanups. So it can be very, very helpful, especially when it comes to inspiring policy and management decisions. In that vein, sorry, I'm moving on because we only have a few minutes left. But what kind of data or information is needed for policymakers to better understand the issue and potential solutions?
So much. I think for me, one really has to do with looking at the various sources. So looking at washing, drying, wearing, in particular, if we just take the garment side of things. And there's an organization called the Microfiber Consortium that's working on a method for testing, essentially like a shedding quotient for textiles and washing machines. And I think that kind of a standardized testing method to understand what's going on is huge. There was like a movement at one point to stop, to just label polyester. And to me, that didn't make any sense. That wasn't based in a lot of information, and because polyester, depending on how it's made, is actually not the thing that sheds the most necessarily. So for me, we really need information to understand what, especially at the gross level, makes our textiles resilient or not resilient, like weave as opposed to just material. So that's one of the things.
I think on that line, better tracking from land to sea. That's why we got into the litter boom study that so I go out on the Great Lakes and I can report on all these microplastics, right? 75% are less than 5 millimeters, and 90% are less than 1 mil. It's insane. And then I report this to communities in and around the Great Lakes, trying to put into place bag bans or bag fees or straws, bans, whatever. And I have, politicians say, well, how do you know it's the bags? How do you know it's the straws? How do you know it's this, right? So it's this connection between what we use on the land and what we find out in the water, and getting better kind of mass estimates of that connection between the land and the water.
We've definitely had a lot of luck in conducting scientific studies, not using citizen science, but scientific studies, compiling comprehensive data sets of the different types of macro trash we found, specifically in the Anacostia River. And that's been a lot of help in passing things like the bag law and the foam ban here in DC. Anyone else have any thoughts on that?
I think the biggest thing that we prioritize, Matt, for these data gaps and understanding is, and we're taking steps towards this, is kind of a combination of what Rachel and Sam are saying, but taking it further is getting a good handle on the source, transport, and fate. Because, Chris is on, one part of the fate side, is in wastewater treatment. We know about transport, but not as well. And it also depends. There's a lot of variables that go along with this. I've always likened the issue of microplastics in aquatic systems to where we were in our understanding of eutrophication 40 years ago, where we thought everything was agriculture based. And that's where the sources of nitrogen were coming from. Well, boy, did we learn. And that was all through data collection and everything. All that said, and I think there is plenty of information, good peer-reviewed scientific reporting and in the literature to make very good policy decisions now. Take a region like the Chesapeake, since that's where we are, we're familiar with. Take a jurisdiction like DC. There are decisions being made without a full suite of data and analysis in hand. It's because you're basing it, you're inferring from what's been done elsewhere. The problem exists to some degree. We don't have all the answers yet. We're trying to get them, but a decision can be made without 100% of the data to back it up. You have to make inferences, and it's done all the time. I'll get off my soapbox.
Anybody else? Okay, I wanted to save this one for last and actually give us a few minutes to answer, because I'm sure several of you have similar or different thoughts about it. But what's the most important question we haven't answered about microplastics? Actually, I'm going to refine that. What's the most important question we haven't answered about plastic pollution? Anybody? Bueller?
I'm going to go, that we're still have a lot of information that, the understanding the impacts on human and ecological health is really kind of the forefront of this research. And it kind of goes back to something that Rachel said of, cotton microfibers versus, synthetic, right? We don't even understand that. Is one better or worse? And we really don't have that kind of data. So to me, I think that's kind of the forefront of this research and really what's important to kind of drive the conversation forward.
And I won't take any more time other to say I agree with every word that Sam just said. That is the same answer, is this impact. What is the impact? We are moving forward because we as in humanity have shown that stuff, things that we thought were great ideas and were going to be okay, turned out not to be as great as we thought. Things like asbestos or lead pipes, where it was okay for a while until we realized it wasn't. I feel like it's the same thing here, but until we have those data, we can only conjecture. So I completely put my vote into human and ecological impacts.
Bob, I'm guessing you have, very strong feelings about this.
Well, yeah. I mean, I agree with what's been said. And we alluded to some of the work that we've worked on over the last 2 years. And I want to try and be concise in how I convey this. One of the items that I think really neglected, I'm a marine ecologist, a fisheries guy. I'm not an economist. And I think we really should get an economist and or an anthropologist involved here, because it's a behavioral issue. And I think particularly on the economic side, plastic is so integrated into our day-to-day lives that I think we have to look at how to extract ourselves. Like Rachel said, we were able to replace lead pipes. We all wear seatbelts now. There's all sorts of things that we've done and we've improved upon, but something like plastic is so, ubiquitous doesn't even cover it. It's so integrated into our lives. And I want to tell you a little anecdote. When I started getting involved more in microplastics work with you and whatnot a couple of years ago, I got an unsolicited phone call from a guy who was from company XYZ. And he was asking me my views on microplastics, same questions we're having here. And, I was like, well, it's an issue, it's bad, it's everywhere, blah, 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 here's the potential. Then he tries to rebuff everything I said. Turns out he was a consultant to the American Chemical Society. And they were going to put out a white paper that said plastics aren't a problem. It's society and how you use them. You're not responsibly using them. And I think we live in an age of disinformation. And that was a great example. So I think the underlying thing here is to looking at human behavior and how can we replace plastic. I don't think we're ever going to get rid of it, but I think there are a lot of things. I might not buy a fleece coat anymore because I know about the microfibers, and I go back to cotton again, or wool for that matter. And I wasn't concise at all.
No, that's fine. That's why I allowed more time for this. I will just say that for anyone interested in a really good understanding of the potential impacts of plastic, I highly encourage you to watch the John Oliver report that came out a couple months ago on plastics. We couldn't play it during the summit for reasons because it's John Oliver, which you can probably guess, but it is very informative. So, Chris, anything from you on this?
I just think, kind of going along with the same things that have been said, you know, we as a society need to, you know, make better choices in the products we use. And, you know, it doesn't have to be drastic. You know, it can be things like, you know, using recyclable grocery bags. You know, I'm sitting at my desk at work here and I'm surrounded by at least 16 different plastics, you know, from my laptop to my cell phone to the pen that I'm writing with. You know, we say the same thing about, you know, pharmaceuticals in the wastewater industry. You know, we have to start making choices as a society into what we use, and, you know, also some public education on the impacts of microplastics and, you know, the choices that we make. Do we throw that dog poop bag on the side of the street and then it goes down the storm drain, or, you know, do we just throw that, you know, plastic bottle out the window, or, you know, yeah.
Very good.
Better choices.
Well, we've got about 4 minutes left. Any closing comments from folks on the panel?
I do. I'll try not to take all the time. I'll try and make it quick. I know Jackie was in the Q&A and mentioning, please do support the Break Free from Plastic Pollution Act. We need legislation. She made a very valid point. You know, I brought up swaps, and swaps are great. It's something that you can do every single day. But what we need is policies that require certain kind of leveling the playing field and make certain requirements of the industry. So I'll mention that, and these whole biodegradable things, these enzymes and microbes that can eat plastic, that's not a solution, and we could spend an entire hour on that. But I'll just say it's not a solution, and allow time for others to talk.
I'll just add that, you know, we're believers in lots of littles make a big. So lots of little problems make a very big, scary problem. But lots of little actions that people take, from swaps to supporting legislation to making changes in one's own life, they all add up. And so and that this isn't all about the people making all the changes. These are also changes that you all, who are decision makers in corporate settings and for various organizations, can, as the deciders, make very big impacts. So this is something that people can make an impact at all levels. And don't be daunted by just a little thing. Just do your thing and then do another thing and another, and it will make an impact.
Well, I'm unfortunately going to have to cut it off there, but I appreciate you guys. Thank you for those wonderful questions. We are going to take a 30-minute break and meet back at 3 o'clock. If you would like to stay with us during the break, we'll be playing more ocean-related musical videos for your entertainment, featuring Jack Johnson and Kev Mo with Taj Mahal. Then a video with Jim Toomey and his cartoon characters, and finally music from Jimi Hendrix. I'm very interested to see how Jimi Hendrix fits into all of this. Otherwise, thank you, and we will see you back here at 3 o'clock.